This lecture is for Module 3 of Unit 3. Unit 3 is the Chemical Kinetics unit, and Module 3 is on mechanism, or descriptions of how reactions work. We will see that mechanisms have a significant impact on rate laws. First, let's consider the case of elementary reactions, or reactions that occur in one step. Elementary reactions basically fall into three types. One reactant A decomposes to go to products. In this case, the rate law will always be K to the power of A, or it depends on the concentration of A. Linearly, it's a first order reaction. There are reactions where elementary reactions where one A reacts with another. Here, the rate law is K times A squared. The reaction is second order. If the reactants are A plus B, the order is second order, and the rate is K times AB. Notice that no elementary reaction has more than two reactants in it, and no elementary reaction is of order higher than second. One-step reactions either occur because of a single molecule process or because two molecules collide. And the probability of three molecules colliding at the same time is very small. So there are only three types of elementary reactions, and if it's an elementary reaction, it's easy to figure out the rate law. Now, any reaction that is more complicated must be a multi-step reaction. Multi-step reactions are composed of elementary reactions that happen in sequence. So here, consider a two-step reaction in which two NaCl's react to make 2NO plus Cl2. Alright, this is not an elementary reaction. As you will see, if this was an elementary reaction, the rate would depend on the square of NaCl, and it would be a second order reaction. However, this reaction goes in two steps. In step 1, NaCl breaks down into NO plus Cl. In the second step, another NaCl breaks down into, reacts with the Cl generated in step 1 to produce NO plus Cl2. Note that the two steps, 1 and 2, add up to the overall reaction. In other words, if we add up everything on the left-hand side of steps 1 and 2 and everything on the right-hand side, the top reaction is the result. Cl that is produced in step 1 is used up in step 2. This means chlorine is an intermediate. More on that in a moment. Alright, you should be able to write down a rate law for step 1 and a rate law for step 2 at this point. Alright, if you've done that, the rate law for step 1, call it R1, is K1, rate constant, times NaCl. It's an elementary first order reaction. Rate law for step 2 is K2 times NaCl times Cl. The observed rate is K times NaCl. K, the observed rate constant, is K1 in this case. We say step 1, had to correct a typo there, is rate determining. Step 1 is much slower than step 2. And since essentially the reaction has to wait for step 1 to occur before the reaction can occur, step 1, the slow step, is the rate determining step. You will see that many reactions, the slowest step is essentially rate determining. The rate of the reaction is the rate of the slow step. Here's another example of a two-step reaction. CH3,3CBr breaks into CH3C3C plus Br negative. This is, you might imagine, a slow step. Then in the next step, the cation produced in the first step reacts with a hydroxide ion to produce a neutral compound. Alright, so the first step is the slow step, where a cation and anion form. Second step is the fast step, where a cation and another anion combine. You should be able to write down at this point, now that we have these two steps, the overall reaction, the rate law for each step, and the overall rate law. You should attempt that before going up. Right, the overall reaction is the sum of the two reactions, and we see this molecule react with hydroxide to make this molecule and a bromide. The rate determining step is the first step, the slow step, and that depends only on the concentration of CH3,3CBr to first order. Rate law for the second step is the concentration of the cation times the concentration of hydroxide anion. Since the first step is step determining, rate determining, I should say, once again, these rate law for the first step is the overall rate law for the reaction. And we have a first order reaction in one of the reactants. Special care has to be taken with the role of intermediates in rate laws. For example, consider this reaction in which two NOs and H2 react to make N2O and H2O. The experimental rate is K times concentration of NO squared times concentration of H2. Now remember that we do not think that three-molecule collisions or three-molecule elementary reactions can occur. Instead, we have two steps, one fast equilibrium step, in which two NOs make N2O2. Now note, because this is an equilibrium step, we have both the forward and the backward reactions occur, and a concentration of N2O2 builds up, which is in a balance with the concentration of NO. The second step, once some N2O2 has been generated by a fast equilibrium process, this reaction going forward and backward, is that N2O2 reacts with H2 to produce N2O and H2O. This is considered a slow step. Alright, so again, first a fast process occurs in which NO reacts with N2O2. This continues until the rate of the reverse reaction and the rate of the forward reaction are close to being the same. You build up a concentration of N2O2, then slowly some of these N2O2s react with H2. If this is the slow step, the rate determining step, the rate of reaction would be K2 times N2O2 times H2. And this would be the overall rate. However, remember, or examine the two steps, you'll see that N2O2 is an intermediate. It's not around before the reaction starts. It's not around after it's over. It is desirable, generally necessary, to remove intermediate concentrations from the rate law. The way to do that is as follows. Consider the fast equilibrium reaction in step 1. Rate law for the forward step is Kf times NO squared. Rate law for the reaction that goes backward is Kb times N2O2. In equilibrium, the rate of production or rate of the forward step and the rate of the reverse step are the same. We set these two things equal to one another. If we do that, we can solve for N2O2. That's Kf over Kb times NO squared. If the overall rate is K2 times NO2, O2 times H2, we can then replace N2O2 in the overall rate law here with the expression we obtained for N2O2 from up here. That produces this expression for the overall rate as K2 times Kf over Kb, H2 concentration, and now the concentration of NO squared has appeared. The intermediate concentration has been replaced with an expression involving reactant concentrations. We can rewrite the overall rate law as R times K times NO squared times H2, where the rate constant K is equal to K2 times Kf over Kb, as seen above. All right, to reiterate once again, we solved this problem by identifying the intermediate N2O2, solving for its concentration, and eliminating it from the rate law. Let's consider the following three-step reaction for a moment. Step 1, OCl reacts with water to make HOCl and hydroxide. Step 2, iodine reacts with HOCl to make HOI and chloride ion. Step 3, IOH reacts with the hydroxide to make IO ion and water. Now, HOCl and OH are intermediates. As we've already seen, intermediates are not there before and after. They are made and used up in the course of the reaction. Water, we have already discussed before, is a catalyst. We've discussed catalysts before. It's there before and after. It's not used up. It's not included as part of the overall balanced equation for the reaction. The balanced equation comes from adding up the three steps. It doesn't include water. Its presence speeds the reaction up. In this case, it speeds the reaction up by providing the first step of the reaction. The water is recovered at the end of the reaction. It's important to be able to identify intermediates and catalysts and not confuse them and not confuse the two. Consider this reaction. HCOOH goes to CO plus H2O. You should be able, from the information provided, be able to determine the rate law, identify catalysts and intermediates. The reaction occurs by these three steps, these elementary reactions. Assume the first one, the fast step, is a near equilibrium step. The slow step, number 2, will again be a rate determining step. The rate law for step 2 is K2 times the intermediate HCOOH2. HCOOH2 is an intermediate, not there before or after. But if one is a fast equilibrium, we can set K1 forward equal to K1 forward times concentration of HCOOH times H equal to K1 backward times HCOOH times HCOOH2. Beg pardon, corrected a typo there. Okay, so again, we write the rates for the forward and reverse equilibrium fast steps as equal to each other. And we can solve for the concentration of the intermediate HCOOH2. It's equal to K1F, K1B times HCOOH times H. Again, we can use this expression to replace the intermediate in the rate law of the rate determining step. That gives this expression for the rate law of step 2. And if we take K2 times K1 over KB is K, the overall rate laws are times K times HCOOH times H. The intermediate HCOOH2 has been removed from the rate law. The rate law does include the concentration of H. So H is a catalyst, and yet it appears in the overall rate law. And that's okay. It's all right for catalyst expressions for catalysts to appear in the rate law. In fact, the rate law now shows that the reaction rate will increase as the concentration of the catalyst is increased. This concludes the lecture on reaction mechanism.